Hey guys, it's Ms. Smith again, and we are going to do the second part of the notes on volumes of solids with known cross sections. So make sure you've watched the first video first, because otherwise this will make no sense whatsoever. But have those notes handy, and we're going to just pick up right where we left off. So let's jump in. All right. Suppose a solid is built in such a way that its base is the region bounded by the curves y equals square root of x and y equals x cubed. If each cross-section perpendicular to the x-axis is a square, find the volume of the solid. Okay, so we've graphed the region here. This is a really small area that's enclosed by these two curves. So we've got y equals root x on top, and then the cubic y equals x cubed on the bottom. So actually between 0 and 1, the square root of x is greater than x cubed for values less than 1 here. Okay, so remember that we discussed in the previous video that we have a 3-step process for volumes of cross sections. And the first step goes with the first dimension, which is length. So for this region, our length is going to be determined by top minus bottom, right? That's coming from the graph. So if I look at the graph, that root x is the top boundary of the region, and this time the bottom boundary of the region is x cubed. So square root of x minus x cubed is going to be my length function that's going to give me the lengths of the sides of the squares as we go through this. So that's it for length, it's just root x minus x cubed. Step 2 of our process is to get something that gives us the area. And our cross sections, we're starting off again with squares. So that top minus bottom, that length, is giving us the side length of squares that are sticking up out of the plane. And this time, right, they start off really small down here. Really, they start off at 0, and they get progressively larger as you go through, right, that those lengths get longer and longer, and so your squares get taller, but then they get small again as we approach this intersection over here on the right. But our cross sections are squares, and the area of a square is just s squared. And this time that side length s is that root x minus x cubed. So we just take that and we plug it in for our side length into the area, right? Because we want our area to be something in terms of x, right? So it's going to be quantity root x minus x cubed, and then all of that squared. So that's our area function now in terms of x. The third step goes with the third dimension, which takes us to volume. So for volume, before we write the integral, we do want to note our intersections on the left and the right. So on the left, we're starting at 0, and on the right, we are stopping at x equals 1. So that's going to be where we start and stop our integral as well. So we just take our area in terms of x, we plug it into an integral from 0 to 1, and then that is it. We're just going to put that on the calculator. So the integral from 0 to 1, and then make sure you're careful on the parentheses, right? So the calculator is going to give you a few parentheses anyway. You then need another set of parentheses, right? And then that root x, make sure that your square root stops before you get to the minus. So root x minus x cubed, all of that in a set of parentheses squared, and then dx, right? So honestly, just typing it and making sure you've typed it correctly is the hardest part. But we're going to round that up. Now we have 0.198, and since we have been going to the second decimal place, and after that 9 is at 8, that means we round up the 9, which rounds up the 1, so that bumps us up to 0.20. Okay, so that was squares. We are going to look at the same region with the root x and the x cubed with our other two cross sections as well. So next up is semicircles, just like we did in the previous part of the lesson. So again, my length, same as before, is just that root x minus x cubed, right? Top minus bottom is going to give me the lengths as we move through here, right? It's going to give us all of those links as x changes from 0 at the bottom up to 1. And then we consider that, okay, our area, we have semicircles this time coming up out of the plane, right? So we've got little semicircles coming all the way along, right? Kind of making this kind of oblong curved figure at the top now. So our shortcut for semicircles is pi over 8 times the diameter squared. And again, the diameter, right, that's what these top minus bottoms are. Those are diameters now of the semicircles coming up. So if that diameter is root x minus x cubed, we just plug that in as the diameter. So we have pi over 8 times that root x minus x cubed all squared. Now you could simplify that, but it really doesn't get like clean or pretty. It just gets really complicated. You would have to FOIL it times itself, and you've got a bunch of roots mixed in with cubes, and it's just kind of yicky. So it really doesn't help anything. So we're just going to leave it like that because we're going to use the calculator anyway. For the volume, last step, as always, again, we're going from 0 on the left to 1 on the right. So we use those bounds. And the pi over 8 can either be, again, it could be inside the interval or outside. That doesn't matter because it's a coefficient. But we put all of that, carefully type it on the calculator, and this one comes out even smaller. But again, keep in mind, right, this whole thing is between 0 and 1, both in terms of x and y. So it's a really tiny little region. So the volume is just 0.08, and that's it. Okay. Next up, guess what? Equilateral triangles. Same base, right? So my length function is going to be exactly the same again. It's just that root x minus x cubed because that's going to give us the side lengths. But now instead of being diameters of semicircles, these are one side of an equilateral triangle, right? So if we take all of these, right, there's going to be kind of like a little ridge that forms along the top. It's kind of hard to see where that goes, but you've got all of these lengths, right, of those triangles, and they're equilateral, even if my sketch is not great. So for equilateral triangles, the area in step 2, our shortcut that we looked at previously, is that root 3 over 4 times the side length squared. Again, the side length is coming from step 1, that our top minus bottom. We just take that, plug it into the square. Again, don't try to FOIL that out. It's really gross. And then our volume, easy peasy, right? 0 to 1. We've already looked at this base. So 0 to 1 with the root 3 over 4. So the only thing that changes if you're switching from a semicircle to an equilateral triangle is the coefficient changes from pi over 8 to root 3 over 4. And actually those values, they seem totally different, right? You've got root 3 over 4, you've got pi over 8. They're actually pretty close. That this volume comes out very similar. So if ever you're looking at one region and then you do, with that one region, you do both the semicircles and the equilateral triangles, the volume should come out pretty close together, right? That we've got 0.09. In contrast with the semicircles of this region, we got 0.08. So they're pretty close together. But that is it for that region. All right, so we are going to take it up one more notch and look at a circular base. Okay, so suppose a solid is built in such a way that its base is bounded by a circle of radius 3 units centered at the origin. And then, if each cross-section perpendicular to the x-axis is a square, find the volume of the solid. So first of all, right off the bat, this region is much, much larger than the previous example, right? Those previous two curves were like right here, and that was like the whole thing. So we got these like really tiny volumes out of it. Now we're going all the way from like -3 over here on the left to +3 over here on the right, and same thing actually in terms of y, because it's a circle. So it's a much larger region. We're going to get some much bigger numbers here. But the process is going to be the same. Length, area, volume. Okay. And we still have cross sections perpendicular to the x-axis, right? So we need to figure out a function that's going to give us these lengths top minus bottom as we go through the figure from -3 on the left to +3 on the right. Now that's weird, right? Because before we had multiple curves, and this time it's the circle going to another part of the circle. So that's unusual. But let's focus on, first of all, how we write the equation of the circle. Okay, so it's centered at the origin and has a radius of 3 units. So centered at the origin is super easy, right? Because it's just x squared plus y squared equals r squared. So starting to figure out that length, we could say, well, that would be x squared plus y squared equals 3 squared is 9. But I want a length function in terms of x, okay? Because all of these cross sections are perpendicular to the x-axis, okay? So we want something in terms of x to give us that top minus bottom. Okay, so I want to take this x squared plus y squared equals 9, and I want to solve that for y equals, because then I will have a function in terms of x. It's just like back when you did circles in the past and you wanted to put them on the TI-84 calculator, right? If you're doing Desmos, you can just type x squared plus y squared equals 9, but if you want to put it on your handheld TI-84 calculator, you needed y equals something, right? And it had to be something in terms of x. So this is the same thing. So if I just subtract that x squared over to the other side, and then if I take the root of both sides, right, what's happening is I need both the positive root and the negative root, right? So in the past, when you've put circles on your calculator, right, and if you just put the positive square root, you actually only get the top half of the circle, but we want both halves of the circle. But it's actually kind of nice for our purposes that the top and the bottom parts of the circle come out separately, because the top and the bottom of the circle are actually the top and the bottom of our length function. So the top part, let me erase some of this nonsense, the top part of the circle, right, so up here, that's the positive root, and the bottom part of the circle is the negative root, right? They're both the same inside the root, but one of those functions comes out being the top and the other comes out being the bottom, so that for my length, if I need top minus bottom, I'm just going to do the positive root minus the negative root, okay? Well, what does that accomplish? Well, if I'm subtracting a negative, then it's just like I'm adding a positive. And if I'm adding a positive and these two roots are the same, if it's root plus root, then it's just like when you do, you know, x plus x is 2x, right? So root plus root is twice the root. So that 2 times root 9 minus x squared gives me the length for top minus bottom. Finally. So it was a bit more work to get that part of the process, but now that we're getting more comfortable, hopefully, with our area and volume parts, now we're ready to go with our shortcut for the square and then plugging it into the volume. So the hard part is over. Next, step 2 is the area. We're doing squares for this first one, right? And area of a square is just side length squared. So if it's just side length squared, I'm just taking that 2 root 9 minus x squared and squaring it. Now, I could take that just as that is, right, just like that, and I could plug that into the integral and it would be totally fine. It's a lot of typing, though, and we can do just a slight bit more algebra before we do that to help us make this be easier to type in a minute, okay? So if I square both the 2 and the root, right, because they're both inside the parentheses, I want to point out right now that I am not distributing an exponent because this is not the distributive property, okay? There is multiplication happening inside this first set of parentheses, which means that both things are getting squared, okay? So exponents apply to all of the parts of multiplication, the way that multiplication distributes over addition. Okay, so just want to make that very clear, right? This is not like distributing to a plus, right? This is an exponent applying to multiple parts of multiplication. So 2 squared is 4, and then on the root, squaring it just gets rid of the root. So the whole area expression just becomes 4 times 9 minus x squared. The root's gone because we squared it out. That 4 times 9 minus x squared is going to be a little easier to punch into the calculator, but again, with that version from earlier with the parentheses of the square, that's fine too, totally fine, because you're putting it in the calculator anyway. Step 3, the volume. So again, just keep in mind, let me erase some of the stuff here, because we've kind of been writing a lot, that your volume, you're going from left to right, and in this circle, that means I'm going from -3 to +3. So take the -3 to +3, set up an integral, take my area function, copy, paste, and then just put it in the calculator. And oh my gosh, it's an integer. How nice. It's just 144. Yes, that's a large number, but as we were saying, this region here, for examples 3a and 3b and 3c, this is a much larger region, right? So when I have squares standing up out of this, they're really tall, right? Over here, they're a little shorter. But they're squares, right? So they have to be proportional to that base. So yeah, it's a large number. It's 144. Now, with all of that having been established, including that length function, guess what? We're going to do the same base again with semicircles and then with equilateral triangles. So we're going to kind of keep that shortcut for the side length, kind of keep that in your back pocket because we're going to keep using it. Okay, so we're going to do semicircles next. So the side length, like we were just saying, we're going to call that d for diameter in a semicircle scenario, right? That we're going to have circles coming up, or sorry, semicircles coming up out of this, right? That as we move along, we're going to have semicircles standing up out of the figure to make a 3-dimensional figure. So the diameter is going to be that 2 root, which means that my area, since this is semicircles, pi over 8 times the diameter squared. We discussed that shortcut previously. So I'm going to take that diameter and plug it in. And again, I can take this version right here and integrate it from -3 to 3 and be golden. That's totally fine. I'm just going to simplify it a little bit just to make it easier to type. Okay? So as we said before, if I square the 2 and I square the root, I end up with a 4 and not a root because I'm squaring a square root, so those cancel out. And that 4 over the 8 can just simplify to be a pi over 2 in front instead of a pi over 8. Okay? The same shortcut as before. You can take the pi over 8 version. It's fine. It doesn't matter. Just making it a little easier to type. Volume, same as before. Left boundary is -3. Right boundary is +3. I'm taking the area and just plugging it into an integral, and that turns it into volume, right? Because it takes all of the semicircles and adds them together. That's what an integral does. It takes a bunch of little things and it adds them together. And there we go. It comes out to be this 56.55, which, by the way, that is actually 18 pi. Okay, now I'm going to go on a tangent here before I switch over to equilateral triangles, because if we think about this, this region, this solid has a circular base, and then it has semicircles coming up out of it. This region is a hemisphere, meaning it is half of a sphere, right? It's a circle on the bottom, it's got half circles coming up out of the top. That is a hemisphere. It has the same volume. So this next part, you don't have to write this down, but one thing that I have said in the past is that one of the kind of fun things about calculus is that it proves and verifies a lot of things that we've kind of taken for granted in previous math classes. And one thing that we took for granted in geometry was a bunch of area and volume formulas. So volume of a sphere is 4/3 pi r cubed. In the past, you were just told that. You were just told that it's this. But let's look at this hemisphere, right? If we take half of that 4/3 pi r cubed, right? If we just divide that by 2 and we simplify it, it just becomes 2/3 pi r cubed, right? For half of a sphere. Or that's what hemisphere means, right? It means half of a sphere. Okay, if we find the volume of a hemisphere with a radius of 3, right? Because we were just looking at a circle with a radius of 3. If I plug that in for r into this hemisphere formula, okay, 3 cubed, if I cancel one of those 3's with the 3 on the bottom, that becomes 2 times pi times 3, which is 18 pi. That's the same thing that we just got from the integral. So a lot of the things for geometry that originally, when ancient Greeks were doing geometry, they kind of just figured out what the formula was by observing it in nature. And then, a few thousand years passed, and then when calculus was figured out, they were able to see where these formulas come from. And here it is. This is why that shortcut works, because this circular base with the semicircles coming up out of it is half of that sphere. And if you take that and double it, you would get the entire sphere. And that's where that 4/3 pi r cubed comes from, which is really crazy if you think about it. But anyway, I just wanted to point that out before we move on to our next shape with the same base. We're going to go back to equilateral triangles. Okay, so back to the same base. We're going to just do equilateral triangles next. So our length formula, same as before, right? Top minus bottom, and we've got the positive root and the negative root. So that comes out to be twice the root, so 2 root 9 minus x squared. And then the area, which our shortcut for equilateral triangles, is just root 3 over 4 times that side length squared. So that's root 3 over 4 times that 2 root, all squared. And again, we can simplify it a little bit. So you can square that out, and then that actually causes the 4's to cancel, right? Because we have 4 on top and 4 on the bottom, so those cancel conveniently. But again, you don't have to simplify that. You can just go with the unsimplified version here. As long as it's in terms of x, then you're good. And then our volume from -3 on the left to +3 on the right. And then we can just put that in the calculator, and that comes out to be 62.35, which again is in the same ballpark as what we got from the semicircle version with the 56.55. So 62.35 for this one. All right, one more. This one's a little weird. So suppose a solid is built in such a way that its base is the region bounded by the curve x equals 4 minus y squared. That's weird, right? That's kind of backwards. So it's bounded by that curve and the y-axis. And then we're going to do each cross-section perpendicular to the x-axis is a square and find the volume of that solid first. Okay, so we have x equals 4 minus y squared and then the y-axis. And the y-axis is just the line x equals 0. So that would be tricky to graph on your calculator, but again, you're welcome to pull up Desmos to do that, as I have done here. Now, we need a function for the late top minus bottom here in terms of x, and we have something in terms of y right now, right? We've got that 4 minus y squared. So we've got x equals 4 minus y squared. That's weird. We want to switch that around, basically, to solve it for y. So if we subtract the 4 from both sides, and then change the sign so that we have positive y squared equals 4 minus x, and then take the root. And it ends up being kind of like the circle, right? Where we have the positive root for the top piece of it, and then the negative root for the bottom. So it actually comes out being both functions. So just like with the circle, right? We have a positive root as our top minus the bottom, which is the negative version of the root. And those two negatives, you could just make them positive, and then it comes out to be twice the root. So it actually ends up very, very similar to the circular base that we looked at before. Okay, so if that's my side length function, twice the root, area, I just plug it into side length squared. Cool, that's it. And then we're just going to take that to root and plug it in. Simplify it or don't. That's a personal preference, right? We can take it just like that as it is and plug it into our integral, or we can clean it up, right? 2 squared is 4 in the front, and then squaring the root actually gets rid of the root in the back. You could even distribute the 4 and just call it 16 minus 4x. This one actually comes out really nice and clean, but you don't have to do that. It doesn't matter. And then the volume, we want in terms of x, right? Left to right. So on the left, because we've got that boundary there, our left is x equals 0. The right, if we just look at the graph, it stops at x equals 4. So our integral is going to go from 0 to 4. And then just take your area function, simplified or not, and plug it in. And then it just comes out to be 32. Actually, it's a nice, happy little integer this time. So 32 is the volume of that solid. And then we're going to do the same base 2 more times, right? Semicircle and equilateral triangles. So with the semicircle, we're going to use that same length formula. We're going to call that the diameter of our semicircles, right? So we've got our little semicircles coming up out of the figure this way, right? So shortcut for semicircles, pi over 8 times the diameter squared, and then we just take the diameter and plug it in. And again, you can leave it unsimplified, or you can choose to simplify it. So if we square the 2 and square the root, and the 4 over the 8 cancels out, kind of similar to what we looked at earlier, and it just comes pi over 2 times 4 minus x. On the left, we've got 0. On the right, we've got 4. So our volume integral is just pi over 2, integral 0 to 4, 4 minus x. And here I've actually done both versions of it with the simplified version and the unsimplified version, just to show that it really doesn't matter, right? The unsimplified is a little more to type. Actually, I didn't even do all the way unsimplified, did I? We could do this version here too. It does not matter. They all come out the same, as long as you simplify it correctly, of course. Right, so we're rounding that, so 12.57 for the rounding. All right, and then one last version of this, right, with equilateral triangles. So got the same base as before, so our length function is the same, right, 2 root 4 minus x. Then for the area, so for our shortcut for equilateral triangles, root 3 over 4 s squared. So we're going to do root 3 over 4 times that side length from top minus bottom squared. And simplify it or don't, it really doesn't matter either way. We can square the 2 and square the root, and then the 4's cancel, which is convenient, right? So that does make it easier to type into the calculator, but unsimplified is totally fine too, as long as you're careful with all the parentheses. And then the volume, right? 0 on the left, 4 on the right. So we just set up our integral. Root 3 can go inside or outside. That doesn't matter either. And then we just put it in the calculator, and this one comes out to be 13.86, which again, just to point that out, that's pretty similar to the previous one with semicircles where we got that 12.57, right? They're going to be pretty close together in the same ballpark for semicircles and equilateral triangles. So that's it, right? We've got the side length, which is top minus bottom, very similar to what we've done in the past. Then for area, you're going to want to know those 3 shortcuts for squares, semicircles, and equilateral triangles, and then you just throw it into an integral and it turns it into a volume. And guys, that's all. That was our last new lesson for on-level calculus for the year. Yay! Congratulations, you made it. Thank you so much for watching. Thank you for your attention, and thank you for sticking with it. I know Miss Bradbury and I are proud of you guys and grateful for all of the work that you have put in. So keep going, see it through, and congrats, guys. Thank you for your attention. Thanks for watching. If you have any questions, let one of us know, and stay safe and be well, guys. Best wishes. Bye.